Okay, Assalamualaikum and hello, welcome back. So today we'll continue with the equivalent circuit of a DC motor, which is focused more on the calculation. So, the equivalent circuit for DC, okay, the field is shown in figure 14. The field current is represented by the RF and LF. Okay, field. Okay, remember you have field and field current and field circuit and the armature circuit. Armature is the rotation part. Okay, field is the circuit that try to create a magnetic field. And for the field circuit, you have R and L. Okay, this one is the field circuit. Okay, this one is the armature circuit. So remember you learned before, you have a VT. Okay, you have VT, the armature current, you have a RA, okay, armature resistance, and then you have EMF, the EA. Okay. Okay, this is the output, the torque, and the angular speed. Okay. So we consider steady state operation in which the current are constant, and we can neglect the inductance because we behave as a short circuit for DC current. Thus, the DC field current we have a VF is equals to RF IF. So what it means that when it is DC, okay, inductor act as a short circuit. There's no function here. So for field current, you only have RF. Okay. So you have RF. So make sure you understand this circuit. Okay. So let me. Okay. Wait. Okay. So this is the stator. This is the rotor. Recall back yesterday. You have stator. You have rotor. Okay. So you can see here. This is the field winding at the outside. Okay. This is the field winding. So this one just represented as this one. Okay. The resistance. Okay, and for the DC rotor, this one, the winding here, it represented as this one. Okay, so you have the RA. Okay, the coil has resistance, so this represent as RA and EA. So when you do when the motor rotates, it will generate EA. Okay, so make sure you understand how this thing represent. So it's just this one and this one. So the EA shown in the equivalent circuit represent the average voltage induced in the armature due to the motion of the conductor related to the magnetic field. Okay, so this one I already discussed before. Okay, this one. So when you apply a voltage VT here, there is a current here, there is a magnetic field, it will move, okay, to the right. Okay. It will move to the right. When it moves to the right, it will also, because you move the conductor against the magnetic field, it will create a EMF. Okay, electromotive force. So it's become a voltage source here. That's why this one occur. Okay. Okay, in the motor, EA is sometimes called back EMF or electromotive force. Okay, back electromotive force. Okay, because it is opposed to the applied external voltage source. So this is also called the back EMF. Okay, you can see here it is against the terminal voltage. Okay, the resistance RA is the resistance of the armature winding plus the brush resistance. Okay, so I mentioned before, okay, inside the coil, okay, when you have a long coil, okay, coil is not perfect. You have a resistance, a small resistance, but if it is very long, the resistance becomes severe, like a transmission line. When it's long, it is much more severe, the resistance. And also you have the brush. Okay, you have a brush. Okay, I don't have the brush. So you have the brush, you also have resistance. So all of it will become RA. Okay, so this one. Okay, but sometimes, okay, the resistance, the drop across the brushes is estimated to be a constant voltage 2 volt rather than a resistance. However, in the Humbly books, we lump the brushes drop with the armature resistance. So depending on book, different theory. So because in this class, in this course, we use Humbley book, okay, we just lump it as a resistance. Okay, this is the induced armature voltage. So this one. So this one, how to calculate this? How to relate EA with the torque? Okay, T is torque, W is angular frequency, okay, or angular speed. Okay, this is how you calculate it. Okay, induced voltage in the induced armature voltage is given by EA is equal to K flux Wm. Okay, so which K is the mechanical constant that depend on the design parameter of the machine. Flux is the magnetic flux produced by each stator pole. Okay, so each pole, and W is the angular velocity, okay, or angular speed. Okay, I suggest you just use angular velocity of the rotor. Okay, so means that the faster you spin, the higher the EA. Okay, K is the constant, flux is the higher the flux, the higher the EA. Then you have a torque. Okay, torque developed in the machine is given by T is equals to K flux IA. Okay, so this is the relationship in which IA is the armature current. Okay, so we will see that the output torque of the DC motor is less than the developed torque because of the friction and other rotational loss. Okay, so your calculate here is much more higher, but after at the end it is much more lower due to the friction and rotational losses. The developed power is a power converted to the mechanical form, which given by the product of development of the torque and the angular velocity. So this is just a standard formula. So if you want to find the power, you just multiply torque with the angular velocity. Thus, this is the power delivered to the induced armature voltage. Therefore, also given by P is equals to EA IA. So if you look here, this one, okay, so you have IA, you have EA, so power, okay, power delivered to the induced armature voltage is given this one. Okay, and then you have to look at the magnetization curve. Okay, a magnetization curve is a DC machine is a plot of EA versus the IF, with the machine being driven at a constant speed. EA can be found by measuring the open circuit voltage at the armature terminal. Okay, a typical magnetization curve is shown in here. So this is the typical magnetization curve. Okay, you can see here, the higher the field current, okay, the higher the EA. Okay, so N is the speed in the RPM, rotation per minute. Okay, so IF, make sure you know what is IF. IF is the field current at the stator. Okay, and this is the EA. Okay, so how to measure EA? Of course, you have to open circuit the voltage at the armature terminal. Okay, so normally at the beginning it is linear characteristic. Okay, but after certain level it will become non-linear. Okay, because EA is proportional to the flux, the magnetizing curve has the same shape as a flux versus IF. Okay, so which depend on the parameter of the curve of the magnetic circuit for the field. Okay, which depend on the parameter of the magnetic circuit of the field. The magnetization curve flatten out for high field current due to the magnetized saturation of the iron. So this is what I meant. Okay, so this becomes saturation, same as the magnetic circuit you learned before. At a certain time, okay, it will become saturated. Okay, of course, different machine usually have different shape of magnetization curve. Okay, so the induced armature voltage EA is directly proportional to the speed. Okay, so if EA represents as the voltage at speed N and EA2 is the voltage at N2, we have this one. Okay, so this is the relationship. Okay, now we move on to the connection. So you have two circuit here. You have a field circuit, you have an amateur circuit. So how we want to connect this circuit? Okay, so the first part is the shunt connected DC motor. Okay, so shunt is actually parallel. Okay, if you don't familiar with the shunt, okay, it's basically parallel. Okay, series is series. Okay, parallel sometimes we call it shunt. Okay, so in a shunt circuit of a DC machine, the field circuit is parallel with the amateur circuit. Okay, if you look here, okay, this one you just parallel it together. Okay, the circuit you parallel it together. Okay, so the field circuit consists of a rheostat, a variable having a variable resistor denoted as RATJ in series with the coil field. Later we will see that the rheostat can be adjusted to adjust the torque speed characteristic machine. We assume that the machine is supplied by a constant voltage source Vt and the resistance of the armature Ra and the induced voltage Ea. Okay, and we denote the mechanical shaft speed is Wm and the developed torque is dif. Okay, so what it means by this, you just add, you can see here, you just add a adjustable resistor to adjust the speed. Okay, so to speed control it, you just combine this together. You shunt the field and armature. Okay, shunt it, and at the field you just add the resistance. Okay, so this one is very useful if you want to control the speed. Okay, where is it? Okay, this one. Okay, okay, it's used to adjust the torque speed characteristic of a machine. Okay, the power flow. So shows that the flow of power in the shunt connection machine, electrical source supply and output is given by this one. Okay, so the input is PTIL. So this is VT. Okay, this is IL. So basically this is the input power. Okay, and sometimes the power used to establish the field is absorbed by the field current converted into heat. Okay, so the heat loss, the field loss is given by Vt squared plus Rf plus this one. Okay, so Vt If. So you can see here, all the energy will go here. Most all the output is here. So basically, what happened here when you add a resistance here, basically it will become losses. Okay, this is not the output. For the field is just to create the magnetic field. Okay, so it will become losses. Okay, this is to a calculation. It's just the V squared, P is equals to V squared divided by R. So in this case, this is the R total. Okay, furthermore, the armature losses occur due to the heating of the armature resistance. So if you look here, this is the voltage. You can use the voltage V squared divided by R to calculate the losses. But for this case, you have to use the current because there is EA. So the losses here you want to calculate is P is equals to IA squared R. Okay, so make sure you differentiate this. Okay, and the power delivered to induced armature voltage is converted into mechanical form and it is called the developed power. So P is equals to IA I EA. Okay, so this one, okay, IA EA, this is all the output power will be produced, and of course power here is equals to mechanical power here. So P is equals to TWM. Okay, P is equals to EA IA WM angular frequency, angular velocity, and T. Okay, and of course remember P out. Okay, this one, this P, and the output torque is less than the value because it is due to the rotational loss, friction, windage, eddy current loss, and hysteresis loss. So the rotational power loss approximately proportional to the speed. Okay, the faster you go, the higher the losses. Okay, so basically the power you calculate here is not the end, so there will be a lot more losses here. Okay, this one I mentioned, so you have a lot of losses after the output. Okay, so this is another figure you can look. Okay, of course you have the field losses, okay, and then you have the armature losses. Okay, due to the RF and R adjust, this one due to the RA, and then you produce the P diff is equals to IA EA equals to TEF TV. Okay, T develop, torque develop, and angular velocity. Okay, and then after that you have a rotational loss, and P out is equals to T out WM. So T develop and T out is not the same. T develop is much more higher than the T out. Okay, because you have to due to the rotational losses. Okay, so this one take into focus. Okay, torque speed characteristic. Okay, so torque speed characteristic is quite an important topic. So applying Kirchhoff voltage law to the equivalent circuit shown in figure 16, we obtain a Vt is equals to RAIA plus EA. Okay, so where is it? Okay, this one. So Vt is equals to RAIA and EA. Okay. Okay, where is it? Okay. So we rearrange it. A is equals to T develop divided by K flux from the T develop equals to K flux IA, and using EA equals to K flux WM, we solve the development of the torque. So KT, okay, T develop equals to K flux divided by RA Vt minus K flux WM. So this is an important equation. Okay, the relationship between torque and speed. Okay. Okay, notice that the torque speed relationship is plotted at a straight line as illustrated in figure 18. So you can see here this one. Okay, if you can see again this equation, this is T. Okay, this one is a constant. You can see here this is constant, and constant. But this is a variable. You can see this is a variable Wm, the torque speed. So this is a linear equation. Y equals to mx. Okay, this is mx plus c. Okay, this is the c part. So that's why it become a torque speed shunt of a DC motor. Okay, when the torque when the speed is 0 means that the motor is stalled. Okay, it's called stall. Okay, stall means doesn't move. Okay, so the stall torque is equals to this one, K flux divided by RAVT. Okay, so at no load speed, okay, no load speed means that there is no load. Okay, so at here this is VT divided by K flux. Okay, so normal operating range is around this location. Okay, so better to avoid this one, because remember that I said it is lower efficiency if you operate at the not a rated, okay, a rated torque. Okay, so sorry, not the at the rated speed. Okay, so make sure you know this. Okay, make sure you know how to draw this. Okay, how to draw the shunt circuit. Okay, this one, this is the shunt circuit. Make sure you know how to draw this, how to label it. Okay, make sure R adjust, RF, LF, KIF, IA, RA, EA, W, and T develop. Okay, make sure you know all the label, and then you need to know how to draw this. Okay, so this will be in your final exam. Okay, make sure you know how to draw this, how to label this. Okay, the stall torque equals to K flux divided by RA Vt. Okay, no load speed is equals to Vt divided by K flux. Okay, so make sure you know the y-axis, the x-axis. Okay, this is the characteristic. Okay, so the speed for no load T developed is T def is equals to 0, and the stall torque are labeled in the figure. So this one I already explained here, stall torque and no load speed. Okay, so you need to know these both parameter, stall torque and no load speed. Okay, stall torque means that W is equal to 0. Okay, no load speed means that T is equals to 0. Okay. Okay, and the normal operating range for most motor are the lower portion of the torque speed characteristic as illustrated. So as I mentioned before, you have to operate at this location. Okay, the starting or stall torque of the shunt connected machine is usually many times higher than the rated full torque. Okay, what this means that during starting, you can see that the W is equal to 0. Okay, but in reality, this stall torque, okay, for shunt connected, okay, for this type of connected, okay, is much more higher than this one. Okay, this is for rated characteristic. Okay, but for starting, it should be much more higher. Okay, so this is the magnetization curve for the motor. Okay, so you can see here the IF and EA. Okay, this one should be the previous one. Okay, the characteristic is almost linear. Okay, and at the end it is starting to saturate. So this is example. Okay, example 16.4. Okay, you can see here this is the supply 240 DC. Okay, make sure this is DC machine, means that the supply is DC. So this is IL. Okay, and IL will divide it into armature current and field current. Okay, so you have R adjust is 14, RF is 10, and LF usually just ignore because this is DC, doesn't mean anything, it's just a short circuit. And then you have IA, RA, okay, armature winding, okay, much more smaller, and then you have a EA. Okay, okay, for the load, the hoist, okay, we are not mechanical students. You are not a mechanical student, so you don't know what is hoist maybe. Okay, but this is the hoist. It's just a device to lifting something. Okay, so may try to know what is hoist. Okay, so the equivalent circuit for separated excited. Okay, this one is for separatedly excited. Okay, maybe for example I will show you. Maybe this node is not organized properly for now. Okay, maybe I will show you the textbook. Okay, you can see here this is the lecture note and this is the textbook. Okay, I will open the textbook to show you some of the example. Okay, so you can see here this is the shunt. Okay, shunt connected DC motor. Okay, how about if you want to excite this system separately? So you can see here this is the equivalent for the separately excite DC motor. Means that your field winding and the armature winding is supplied with a different source. Okay, so you can see here this is VT, the supply for the armature, and this is another supply for the winding, field winding. Okay, so you have two supply. So this one is called separately excited DC motor. Okay, so your speed can be vary either the by varying either the voltage source for VT or VF. So if you recall back, wait, I pause first. Okay, you can see here you can vary. Okay, if you vary the field, okay, field winding, you can increase the flux. Okay, you can increase the flux, or you can vary the EA, you can vary the vary the VT, and you can vary the EA. Okay, so you can control the torque speed by applying two different voltage source. Okay, so this is the separately excited DC motor. Okay, how about a series connected DC motor? So you have the third connection type. Okay, series connected DC motor. Okay, if you want to see, it is just in series. The field winding and the armature winding is in series. Okay, so you can see here, this is the field winding. Okay, your winding here, you just connected in the series with the armature, so it will become a series connected DC motor. Okay, so notice that the field winding in series with armature. In this section, we will see that the series connected lead to a torque speed characteristic that is useful in many applications. Okay, basically the connection of the DC motor between the armature and the field winding is basically depending on the application. So if you recall back the first slide, okay, so slide number 13. Okay, so you can see here you have the shunt, you have the series, you have the compound. Okay, the separated I think there is not available here. So you can see here for shunt, industrial application for grinding, machine tool or hoist. But for series is for high torque and low speed application. Okay, so if you have a high torque, you need a high torque, but low speed, it's better to use a series connected. Okay, and make sure you know that it is for series connected. It is very dangerous if you don't connect the no load. Okay, if there is no load, can be very dangerous. Okay, so in series motor, the field winding are made of a larger diameter wire, and a field resistance are much more smaller than those of in the shunt machine compared to the size. Okay, so what is mean that, okay, let me show picture. Okay, for this part, this winding is much more larger. Okay, because of it is larger, so the RF is much more smaller. Okay, so if you compare series connected or shunt connected, okay, this is necessary to avoid too much voltage drop at the source voltage across the field winding. So why we have to use larger winding? Okay, because if you use larger winding, RF is smaller. You know that the diameter of the wire, the larger the diameter of the wire, the smaller the resistance. Okay, that's why we have to reduce it, because we don't want to have a voltage drop too many at this winding. Okay, this one. Okay, so we don't want too much voltage drop at here. Okay, and make sure you know how to draw this. Okay, series shunt. Okay, separately shunt also you need to know how to draw this. Okay, just separate. Okay, and then too many wait. Okay, so torque speed characteristic, of course we use a linear equation to approximate the relationship between the magnetic flux and field current. So in this equation, you have the flux is equals to KFIF. So if you recall, Ni is equal to something. Okay, recall the magnetic circuit. Okay, so that one is much more complicated. So we just simplify it into a constant here, Kf, IF. So this one is the N. Okay, if you recall back, and what else? The area and everything. Okay. So you just flux is equals to Kf, which Kf is a constant depending on the number of winding, geometry of the magnetic circuit, the BH curve of the iron. Okay, so of course the relationship is not linear. Okay, due to the magnetic saturation. Okay, if you recall, there are magnetic saturation. Okay, a plot of flux BF versus IF has exactly the same shape as the magnetic curve. Okay, of the machine. So if you recall back, try to recall back your magnetic circuit. Okay, so it's just a simplification of this. Okay, So because IA is equals to IF, because it is in series, you can see it here, IA is equals to IF, this is in series, the series machine, we have flux is equals to KFIA, and subsequently flux is EA equals to K flux WM, and T developed is equals to K flux IA. Okay, so from this, okay, if we apply Kirchhoff voltage law in the circuit here, we can see that VT is equals to RF IA RA IA plus EA. Okay, so just do a Kirchhoff voltage law here. You can see here, this is IA. Okay, assume that this is all IA. So the resistance, this is just ignore RF IA RA IA and then plus EA. Okay, this. Okay, and solving this, you just make the IA at this one location. So you can see here, IA is equals to VT divided by RA, RF, and KF, WM. So make sure you know the difference between this constant, okay, and this constant. This is a different constant. Okay, you can see here, this is K, normal K, and this is just a machine constant. Okay, and this one is KF, which is the field constant if not mistaken. Okay, so this is a different constant. So the final one is T is equals to KF V squared divided by this one. Okay, make sure you know how to derive this. Okay, you just insert this relationship. Okay, so you already use Kirchhoff voltage law. You find the IA in there, IA insert to here, you get the answer. And for this one, you just insert EA. Okay, so this is the final equation. Okay, if you plot this, this is the torque. Okay, torque speed relationship. Okay, you have torque, you have speed here. All of these are constant. You can see here, this is constant, constant, constant. Okay, constant. And this one is considered constant. Voltage source is usually we just a constant one for series and shunt connected. Okay, so a plot of torque versus speed for the series motor is shown in figure 23. So you can see here, this is the relationship. Okay, from this one. Okay, so from this we plot this. Okay, you get the starting torque. Okay, is quite high. Okay, this is the starting torque. Okay, you just make W is equals to 0. So you can see here, W just make it into 0. Okay, and then you just plot it, you get this one. Okay, okay, this is starting torque for the calculated one. But of course, remember you have a saturation effect. Okay, the BH curve, remember iron will be saturated, so it will be lower than this saturation effect. Okay, should be lower. Okay, okay, and then you have a rotational loss and everything, it will become lower. This is the real one. Okay, this is based on the equation. Okay, so this one, if the speed is to infinity, you can see here. Okay, it will become, okay, the torque becomes smaller, 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 but in reality it will be drop. Okay, okay, the figure show here the plot of equation 34. Okay, as well as an actual curve of the torque speed. Okay, this illustrated effect of the rotational loss and magnetic saturation. Okay, so this one already mentioned here. What is the effect? Okay, so magnetic saturation, it will reduce the starting torque. Okay, or this one. Okay, starting torque. Okay, it will reduce it. And then the rotational loss, because of the rotational loss, it will not follow too close. It will not follow closely. It will follow closely, but not same. Okay, so and make sure you know how to draw this. Okay, equation 34. Okay, predicts the infinite no load speed. In other words, t is equal to 0. Okay, the speed must be infinity. But the speed is lost. Okay, there are power losses. That's why it's not goes to infinity. Okay, if the t is equals to 0, it's not, the speed is not infinity, it will be reduced. Okay, so yet the high speed, okay, this one already explained. However, in some case there is no load, speed can become large enough so that is dangerous. Okay, so be careful, that's why in the, okay, this one, okay, dangerous if not loaded. Okay, why? Because in series connected DC motor, okay, if there is no load, the speed can be very fast. Okay, make sure you have a load when you run a series connected DC motor. Okay, so at the very low speed, equation today shown that the current IF is equals IA become large, then magnetic saturation occur. Okay, therefore starting torque is not as large as predicted in equation. This one already explained, this one. Okay, okay, let's move on to the next part, speed control of a DC motor. Okay, when it comes to DC motor, several methods can be used to control it. Okay, so first one, by varying the voltage supply to the armature circuit while holding the field constant. So this one, I think this is the separately excited. Okay, so this one is much more suitable for separately excited. Okay, and then vary the field current while holding the armature voltage supply. Okay, this one also same. Or insert a resistor in series with the armature circuit. So this one is parallel. Remember, you have R adjust. Okay, this one R adjust. You insert the resistance, okay, to control the speed. Okay, so where is it? Okay, this is 3 ways to control the speed of a DC motor. Okay, so let us look. Okay, variation the power supply. So this method applicable to separately excited motor, as mentioned before. Okay, if you have a separately excited motor, this one. Okay, this one. Okay, you can vary the voltage here. Okay, this one and this one. Okay, to control the speed. Okay, okay. And for shunt motor, by varying the voltage supply is not appropriate method to control the speed because the field current and flux vary with the Vt. Okay, so remember, if you are parallel, okay, your field current and the flux will vary with Vt. The effect increase both armature supply voltage and field current tend to offset one another. Okay, which result in a little speed change. So for shunt, so if you varies the voltage here, it is not suitable because you have the same source to control the field, okay, and the EA. So if you use the voltage source variation, it will not have too much effect. Okay, that is the limitation of the shunt connected if you vary the voltage source. Okay. Okay, in normal operation, the drop across the armature resistance is small compared to EA. We have EA is almost equals to Vt. Okay, since we have EA is equals to, okay, flux, okay, Wm, we can write that W is equals to Vt divided by K flux. Thus, the speed of separately excited motor with constant field current or the PM motor approximately proportional to the voltage. So this one PM is a permanent magnet, means that you don't have a current for the field. You have a naturally occur magnetic, okay, permanent magnet. Okay, so this one will have the fix this one. Okay, so you can see here the relationship. If you varies the Vt, okay, you can varies the speed. Increase the Vt, increase the speed. Okay, this one is suitable for separately excited motor or PM, permanent magnet. Okay, variation of the voltage supply also appropriate for the control of series connected DC motor. However, this flux doesn't remain constant in this case. Equation shows that the torque in series machine is proportional to the square of the source is at any given speed. Thus, depending on the torque speed characteristic, the speed vary when applied voltage. Generally, higher voltage produce higher speed. For series connected, you also can use voltage control. No problem. Only the problem is the shunt. Shunt connection. And also you need to know that the higher the voltage, the faster the speed. Okay, so make sure you know why the shunt motor, the shunt type shunt connection is not suitable for varying voltage supply. Make sure you know. You need to know how to explain this. This is a very important topic. So the shunt, this is the series. The shunt, you need to know how to draw. Make sure you know how to draw this. How to draw the circuit. So I would like to remind you again. Make sure you know how to draw the circuit. Make sure you know how to draw this. And then you need to know how to explain why. Why it is suitable, is not suitable. For this case, the different one is the shunt type. Shunt type is not suitable for the voltage supply variation. So make sure you know. So this chapter is more towards the theory. You need to know the theory. So we continue with the next part. Instead of varying the speed, varying the voltage supply VT, you vary the field current. How to vary the field current? What is field current? So I think you already know, you already seen too much of this. This is the field current IF. Varying the field current, you varying the flux. Same here. This is IF. This is shunt type. This is IF. So by varying the field current, you can speed control. The speed for either shunt connected or separately excited motor can be controlled by varying the field current. So shunt and excited, separately excited motor, is suitable for field current type. The circuit for the shunt connected machine was shown in figure 16, which rheostat RADJ is added. So you have added the RADJ. So you can see here, this is additional resistance you add. When you, this is the same voltage source. So when you increase the resistance here, so VT is IF is equals to VT, same parallel. VT divided by R adjust by RF. So because of that, if you increase it, you reduce the IF, field current. So if you reduce the field current, you reduce the speed. So basically, increase resistance, reduce, increase resistance, reduce current, reduce speed. On the other hand, permanent magnet has a constant flux. So if you have a permanent magnet, means that there doesn't need power, additional power. It's just a permanent magnet. You have a constant flux. In a series connected motor. So this one, what it means that you cannot control the permanent magnet by varying the field current. There is no current. Permanent magnet doesn't need IF. So you cannot control speed with the permanent magnet. And in the series connected motor, the field current is the same as the armature current. and it cannot be independently controlled. Thus, using the field current to control the speed is not appropriate for other of this type. Okay, so you need to know for speed control by varying the field current are only suitable for separately excited motor and the shunt connected. For PM, permanent magnet, and the series connected, you cannot use this. Okay. Okay, another one is inserting resistance in the series, okay, with the armature. Okay. So this one, okay, this one is not the RADJ. Okay, wait ah. So this is not R adjust. So that is means that you add a additional resistance here. Okay, or add the additional resistance here for a separately excited, or add an additional resistance here. So basically you just add a resistance, okay, at the armature. Okay, so this approach can be applied for all types of motor, okay, shunt, separate, series, permanent magnet, all of it is suitable. Okay, I already show you how to add it, where you have to add it just in series with the armature circuit. Okay, now you increase the resistance. Okay, okay, RA. Okay, so basically when you add additional resistance, your RA will increase. Okay, so basically if you use the relationship, the equation here, you can get the relationship. Okay, so this is the shunt type, shunt connected. So you increase RA, basically you reduce the torque. Okay, so plot the torque speed characteristic for the various resistance as shown in figure 26.b. Okay, similar result applies separately excited EM motor. So you can see here, if you decrease the RA, okay, you add a RA here. Okay, you decreasing the RA, okay, the lower the RA, okay, the higher the shunt torque, okay, the stall torque. Okay, so you can see here, increase. Okay, and this one, the no load speed is maintained the same. You only have to see that it is decreasing right here. Okay, so make sure you know how to add the circuit. Okay, how to show the effect. Okay, this is for the series motor. Okay, oh, it doesn't show. Okay, okay, it doesn't show. Okay, so this one you just, okay, if you make RA made larger, adding resistance with series with armature, the torque is reduced for any given speed. Okay, so you increase the RA, okay, you reduce the speed. Okay, so that's it for the motor control speed. Now we move on to the next part, which is DC generator. Okay, before I forget, so one more thing you need to know, that for shunt, okay, okay, for shunt, what happen if you disconnect the field? Okay, disconnect the field winding. So when you disconnect this, you can see here, if you disconnect this, IF will equals to 0. And if you recall, if IF is equals to 0, okay, so IF is equals to 0 means that the flux is equals to 0. Okay, as a result, EA equals to 0, TDR develop is equals to 0. So make sure you know what happen if this is disconnected. Okay. Okay, so we continue with the DC generator. So generator converts kinetic energy from the prime mover, okay, such as a steam turbine or diesel, into electrical energy. When a DC is needed, okay, DC power is needed, we can use the DC generator or AC source combined with the rectifier. Okay, so the trend is towards the AC source and rectification. However, many DC generator is in use for some application. Okay, so this one is just a general. Okay, usually, okay, if you want to use a DC, okay, you want a DC source, okay, we don't use a DC generator, we usually use a AC source, and we rectify it. Rectify is basically change AC to DC. Okay, so but sometimes the DC generator has its application. Okay, several connections illustrated in figure 29 are useful for DC generation. Okay, DC generator, we will discuss each of the connection briefly and conclude what is example illustrated for performance calculation separately excited generator. So you can see here, this is a DC generator equivalent circuit. So you have a prime mover, you have a RA, IA, IL. Okay, so this is the load. Okay, so this is basically separately excited. So you can see here, okay, you have a VF. Okay, so you have the field. Okay, this field will produce flux for the EA. Okay, so something like this. Okay, and you have the shunt type. Okay, for shunt type you have a prime mover. Okay, this one is EA. Okay, it will produce the IA, RA, and then it will produce the flux. Okay, and it will generate current. Okay, so this is a compound connection. Okay, compound means that you combine series field and shunt field. Okay, you have two field. Okay, so this is some example of DC generator equivalent circuit. Okay, separately excited DC generator. Okay, the equivalent circuit for the separately excited DC generator is shown before here. This one. Okay, prime mover drive the armature shaft at angular speed Wm, and external DC source. Okay, you have to have external DC source. So you can see here, you need to have an additional source. Okay, to produce the field. Okay. Okay, supply current IF to the field coil. The induced armature voltage causes the current to flow through the load. Because of the drop voltage of the armature resistance, the VL decrease as the load IL increase. Okay, assume that constant speed and field current. Okay, so you can see here. So when you increase the load, okay, increase the load, so IL increase. So the voltage at IL will reduce due to the voltage drop at RA. So you can see here, this is RA. So when you increase the current, you increase the voltage drop here, the voltage here will be reduced. Okay. This is separately excited or shunt connection. Okay, this is the limitation. Okay, how about the compound connection? So this is cumulative, this is differential. So it will look something like this. Okay, so this is VL, this is IL. Okay, for some application, it is describable for the load voltage to be nearly independent of the load current. A measure of the amount of decrease in load voltage in the current is voltage regulation. So you already know this one. So this one, the larger the voltage drop, okay, the poor the system is. We want to make sure that the voltage regulation is much better. Okay, so I think this one is much more better because you can see here, but this increase something like this. Okay, this is quite bad. Okay, so in which VNL is no load voltage, IL is equal to 0, and VFL is the full load voltage. One of the advantages of separately excited DC generator is that the load voltage can be adjusted over a wide range of varying field current, either changing the VF or changing the R adjust. Okay, also the load voltage is proportional to the speed. Okay, so this is the advantages of separately excited. Okay, so if your voltage is dropped too much, you just increase the VF. Okay, So performance calculation separately excited DC generator. Okay. So for DC motor, following equation is for DC. Okay. So EA is equals to constant flux Wm. Okay. T develop is equals to K flux IA. Okay. This is the standard one. Okay. You can use the Kirchhoff voltage law. Okay. So you get this one and you include this. So you can get this one. Okay. VF is equals to this one and this one. Okay. So this is the, okay, you apply the Kirchhoff voltage law here. Okay, from this you can get the efficiency. Okay, P out, P in. Okay, you can get here P in is the T flux Wm, and then you have a friction, eddy loss, hysteresis, amateur loss. Okay, almost the same, just reverse it out. Okay, okay, that's it for DC. Okay, calculation. So actually you have to look more on the practice side. Okay, so for practice side you have to look at this one, this book. Okay. Okay. Okay, you have a various example here. Okay, I will show you after this. Okay, so see you in the next video.